Right, we've had a lot of look at sketching sine and cos functions, right? So now it's the time for tangent functions. So we're going to start off with solving some tangent equations, and then we're going to move into sketching some tangent functions at the later part of this lesson. Right, so they want us to solve the equation tan 2 times x minus pi on 3 is equal to 1 for the domain x is equal to 0 to 2 pi. Right, so the first thing I want to emphasize here is, unlike our sine and cos functions, the period of a tan function can be worked out by pi divided by n. So tangent functions basically repeat itself after every pi units on the unit circle. Right, so to start off this particular question, right, tan 2 times x minus pi on 3 is having a period of pi on 2, because the value for n is 2 in this case. So this one's got a period of pi on 2, which means in the domain that we're trying to solve for x, we'll be able to fit 4 cycles. So we're going to have 4 cycles that can be fit in terms of the tangent functions within the domain that's been given to us. Now, unlike sine and cos functions, because our period is 2 pi units, we have 2 solutions every single time we go around the unit circle. Tangent function having a period of pi over n, it's only going to have one solution per cycle. So let's start off with this, right? When is tan equal to a positive 1 in the first quadrant, right? So in the first quadrant, the angle that's going to give us the value for the tangent ratio to be equal to 1 is pi on 4, or 45 degrees, right? So which means the solution we're going to have is 2 times x minus pi on 3 is equal to pi on 4. Now, like I mentioned to you earlier, right, so CAST, which is the 4 quadrants where the ratios are positive, right, now tan is positive in the first and the third quadrant, right. Now, when we dealt with sine and cos, we've always dealt with an angle in the third quadrant to be pi plus theta. Now, because tangent ratio repeats itself after every pi rotations, we don't actually have to worry about this. We're just going to simply find consecutive angles by just adding the period of the tan functions, right? Right, let me get to that. Hopefully, I'm hoping not going too quick, right? So dividing both sides by 2, so if I divide both sides by 2, I'm going to have x minus pi on 3 is equal to pi on 8, right? So adding pi on 3 units to both sides, right? So if I add pi on 3 units to both sides, obviously we notice the denominators are different, right? Which means we're going to make them the same denominators, right? With the lowest common multiple being 24. So 3 plus 8, that's going to be 11 pi on 24 is my very first solution for this particular tangent function, right? So now that we've got the solution for we've got one solution, we can find the consecutive ones by basically adding and subtracting the period of this particular tangent function. The period is pi on 2, so I'm simply going to go 11 pi on 24 plus the period, which is pi on 2. Right, if I make the denominators the same, that's going to be, what's that? That's 12 pi on 24. So that's going to give us 23 pi on 24. Right, so that gets me to my second solution in this particular case. Now remember, we talked about we could have up to 4 solutions. Now if I go to find my next solution, I'm going to add a period to it, so x is going to be equal to 23 pi on 24 plus pi on 2. Alright, so pi on 2 in terms of a denominator of 24 is 12 pi on 24. Right, so that's going to give us 35 pi on 24. Right, that's going to be my third solution. Right, and we could possibly get a fourth solution by going x is equal to 35 pi on 24 plus pi on 2, which is going to lead us into 47 pi on 24, right? Given the denominator is 24, a value of 2 pi is basically equal to 48 pi on 24, right? So which means that gives us the final solution to this particular question, right? Now, like I've done in the previous examples for sine and cos equations, we are going to rewrite all the solutions in the ascending order. So x is going to be equal to 11 pi on 24, 23 pi on 24, 35 pi on 24, and finally 47 pi on 24. Alright, and that solves the tangent equation 2 times tan of 2 times x minus pi on 3 is equal to 1. Right? That's where we are with this particular question. Right, let's move on to a second example. Right, this time we're going to go into sketching a tangent function. So we're just going to sketch the graph of each of the following function between the domain 0 to 2 pi. So the equation that we have is 3 times tan 2 brackets x minus pi on 4 take away 2. Right, now if I look at all the individual aspects of this particular scenario, right, unlike the sine and cos functions, the tangent function basically has asymptotes. That's because we have some values of tan where the ratio is undefined, right? So, like for example, tan pi on 2 is undefined, and tan 3 pi on 2 is undefined. So there's a lot of values in tan where we have an undefined answer, which means we have the presence of an asymptote, right? What that means to us is, unlike sine and cos functions, the amplitude of the tan functions doesn't necessarily play a very significant role in the way the sketch appears, right? Because we go all the way from negative infinity to positive infinity before we get to the asymptote, right? So that's why the amplitude of this particular tan function is equal to 3, right? Now the value for n is equal to 2, which means the period of this particular tan function is going to be equal to pi divided by 2, which automatically gets me to the domain that we're sketching in. I can see I can fit 4 cycles of this tangent function, right? We've got a horizontal shift or a phase shift of a positive pi on 4 units, so we're going to move to the right direction by pi on 4 units. We also have a vertical shift of minus 2, right? So which means you're going to move down by 2 units, right? Now, unlike sine and cos functions, a tan function is always going to have an x-intercept. The reason being because of the presence of the asymptote, where you might go all the way from positive infinity to negative infinity. Right, what I mean by that is I'm just going to quickly draw a rough graph of tangent function, right? So if I just have a tangent function, so the basic one, so y equals tan x, for example, right, which has a period of pi, right? It has an asymptote at pi on 2, right? So we're going to go from 0 all the way to infinity, and then from negative infinity back to 0, right? That completes one complete cycle of the tangent function, right? Given the fact that the graph goes all the way to infinity and we come from negative infinity back to the starting value, right? Doesn't matter what my vertical shift is, at some point it's going to cut the x-axis, right? Which means a tangent function is always going to have an x-intercept irrespective of what the vertical shift is. Alright, so which means, let's go back to this question, right? We need to find my x-intercepts for this tangent function, right? So that's what I'm going to do. So to find my x-intercept, we're going to go y equals 0. Right, so if I go y equals 0, so that's going to give us 0 equals 3 times tan 2 brackets x minus pi on 4 take away 2. If I make the tan ratio the subject, I'm going to have tan of 2 times x minus pi on 4 equals 2 on 3. Right, now we have sort of hit a brick wall here just because of the fact that the values that we've dealt with in the first quadrant, none of the angles, whether it was 0, 30, 45, 60 or 90, is going to result in a value of 2/3 for the tan ratio. Right? When we stop at a situation like this, right, the only way we can work out the x-intercepts for this particular tangent function is with the help of our CAS calculator. So that's what I'm going to do next. I'm going to fire up my CAS calculator. Right, so we're going to go straight to our CAS calculators. Right, I'm going to open up, you can open up a graphing page as well, but I'm going to open up a calculator page. And again, most importantly, make sure your calculator's in radians. So we're going to go menu, algebra, solve. Right, we can write the original question the way it is, or we can write the statement that we have at the very end. So I'm going to do that. So tan of 2 times, right, we've got to use x minus, bear with me, I'm just going to go back to the question, pi on 4. I'm going to do control divide, Right, so pi on 4 equals 2 on 3. Right, we are solving this for x. I'm going to put a comma x. Right, we need to come outside the bracket. Right, this is where we got to specify the domain, because if we don't specify the domain, the calculator is going to throw up a general solution. So the domain is, so we're going to go control equals the vertical bar 0x is greater than or equal to 0, but less than or equal to 2 times pi. So 2 times pi. If I press enter, I do get a weird solution. So I'm going to go do control enter. Alright, so we got tan of 2 times x minus pi on 4 equals 2/3. And that is the solution we have. The reason why we have a weird solution is I've just made a mistake in the statement. I haven't quite clicked less than or equal to there, so I'm going to do that. Right, hopefully that gives us a better solution. Right, yes, I hope so. Right, I'm going to do it as a decimal values that way. Right, so we've got 4 solutions, so 1.07, 2.65, 4.22, and 5.79. So 4 solutions, 4 cycles, right? Remember we talked about that. Right, so I'm going to go back to my statements there. Right, let's not worry about writing those values down for the moment. Right, let's go straight into the sketch of this particular tangent function. Right, my period is pi on 2, my horizontal shift is pi on 4, right? Obviously the lowest common multiple being pi on 4. We're going to split each of the units of this particular graph in the x-axis based on pi on 4 units, right? So that's what I'm going to do, right? I'm going to go all the way up to 2 pi, right? So we're going to have 0, right? How many boxes do I have? I've got 1, 2, 3, 4. Obviously I'm not going to be able to fit it, so we're going to take each box as pi on 4, so that's going to give us pi on 2, pi, 3 pi on 2, and 2 pi, right? So which each values being my horizontal shift, in other words, right? Which is pi on 4 units, right? So each box on the x-axis is pi on 4 units, right? You can so there's a vertical shift of -2, so we're going to have a vertical shift of -2. So there we go, right? Now the period is pi on 2, right? The asymptote's basically halfway in the period. So if I divide that by 2, so I'm going to have pi on 2 divided by 2, which is going to leave me as pi on 4. So if I decide to sketch this function without my horizontal shift, right? If I decide to sketch this function without my horizontal shift, I'm going to have my vertical asymptotes at these particular values here. So pi on 4, we complete one cycle. Right, and then we have the second asymptote for the second cycle, third one for the third, and the fourth one for the fourth. Right, so that's the way we're gonna flow if we didn't take into account my horizontal shift. All right, but given we have a horizontal shift, so I'm gonna rub off those asymptotes. All right, so we have to take that into account. So what I mean by that is instead of starting at 0, we're gonna start the tangent function at pi on 4 units to the right, so which means the first point in that tangent function is going to be at pi on 4 units at the mean value, right? Which means everything shifts to the right by pi on 4 units, which means our asymptote, the very first asymptote, is going to be at pi on 2 instead of pi on 4 because it's shifted to the right by pi on 4 units, right? And then our second cycle finishes at this particular point, right, leaving us with my second asymptote, right, at pi, then my third asymptote at 3 pi on 2, and my fourth cycle's asymptote is going to be at 2 pi. Now I also need to take into account that my asymptote is also going to be at the y-axis. The y-axis is also going to be an asymptote in this particular scenario, given we have a horizontal shift, right? So now let's quickly sketch this one, right? So positive tan, so going up first, right? And coming from negative infinity back to the center, right? That's one cycle with a horizontal shift of pi on 4 units. Because remember when we did this spacing of units, we took one box on the x-axis as pi on 4, right? So shift to the right by pi on 4, right? Let me just go back and finish this graph. So second cycle, right, third cycle, and the fourth cycle is not going to complete on that side because we go past our domain for this question. And then we go back to the very starting value. It's going to continue down to the left as well. So that completes my 4 cycles of the tangent function with my horizontal shift of pi on 4. So what I've done here is I've basically sketched my my function of what is the function again? Sorry, 3 times tan 2 brackets x minus pi on 4 take away 2. Right, now if you want, obviously we have worked out our x-intercepts using the CAS calculator, so you can actually mark these x-intercepts in your graph the way it is. The first one being right, the first one being x equals 1.08, right? So 1.08. Right, so you can mark it at that particular value, so 1.08. You can choose to that, given the situation that it is not a value in the first quadrant. If this question does appear in a non-calculator section, they are not going to be worried too much about the x-intercept, right? But if this particular value here was a value in amongst the table of values in the first quadrant, then we would actually have to work out the x-intercept for the tangent functions without the calculator, just like how we solved for this particular tangent equation. So, you know, in that sketching example, we had the tan value equals 2/3, which is not a value in that first quadrant, but in this example we had it equal to 1, right, which is a value that we know in the first quadrant. So in a scenario like this, we will have to follow what's going on here to solve for the x-intercepts without the help of a calculator. All right. Right, one last example in this section, right? So solve the following equations between 0 to 2 pi when we have sine 3x is equal to square root 3 cos x, right? So we have two different functions, sine and a cos function. They're equal to each other. We got to solve this equation for x, right? So the first and foremost step is what I'm going to do is I'm going to divide both sides by cos x. Right, we're going to divide both sides by cos 3x, right? So if I do that, I'm going to get on the left hand side sine over cos, which we know is equal to tan. So tan 3x is equal to the square root of 3, right? And we know by the values in our first quadrant, tan is equal to the square root of 3 when the value for the angle is equal to pi on 3 units. So when it's equal to pi on 3, tan is equal to square root 3, which means we get 3x is equal to pi on 3. Alright, solving for x gets me my very first solution as pi on 9. Alright, now I just forgot to mention something, right? We got tan 3x function. Tan 3x function's got a period of pi on 3, right? Which means in the domain 0 to 2 pi, right, we should be able to fit 6 cycles, right? Which means we should have 6 solutions for this particular question, right? So in every cycle we're going to have one solution, so 6 cycles going to result us in 6 solutions, right? We can quickly find that out by just adding the period to the very first one that we have. So the next one's going to be x is equal to pi on 9 plus pi on 3, right? That's going to be equal to 4 pi on 9, and then we can keep going forward in that fashion. So 4 pi 3. Right, so going forward in that fashion is going to give us all the 6 answers as pi on 9, 4 pi on 9, 7 pi on 9, 10 pi on 9, 13 pi on 9, and finally 16 pi on 9. Right, none of these fractions can be simplified any further, so we're just going to leave the way it is. Right, I know it's been a long lesson, Thank you for watching. Thank you for your patience. Have a wonderful day.